Hello everybody, in this lecture we will be solving 1993 IMO problem number 4. Here is a view of this problem. For 3 points P, Q, R in the plane, we define M of PQR as the shortest altitude of triangle PQR, and if the points are collinear, making a degenerate triangle, then the shortest altitude obviously would be 0. Prove that for the points A, B, C, and X in the plane, the following inequality holds. For this, after working out a few examples, one would recognize there is basically 3 cases. So the cases can basically be listed as: the first case would be where X, you have a triangle ABC and X happens to be inside that triangle, and you would have to compare the shortest altitude of triangle ABC, with that of the shortest altitude of XBC and the others, and ABX and ACX. Another configuration would have X on one vertex, A and B on the other, and the remaining vertex, let's say C, on the inside the triangle. That's the second configuration. And the final configuration would be all four constituting a quadrilateral, a convex quadrilateral. So we'll go in fact in that order. So let's start with the first case. What happens if X is inside or on the boundary, actually inside or on the boundary of triangle ABC? So case 1, X is inside or boundary of triangle ABC, mainly the first case here, the first picture drawing. Let me introduce some notation. Let delta 0 represent let delta 0 represent triangle ABC. Delta 1, I would let it represent triangle XBC. Delta 2 would represent triangle AXC. And finally, delta 3 would represent triangle ABX. Now recall that M of delta I simply represents the shortest altitude of triangle I. And let's also introduce 2 more notations. Let A sub I represent the longest side of triangle I, and let also S sub I represent the area of triangle I, and this holds for all I between 0, 1, 2, and 3. Finally, let's make the following observations now. First of all, obviously, the longest side of triangle ABC, in that case A sub 0, will definitely be greater than or equal to the longest side of the remaining 3 smaller triangles, right? These 3 triangles combined make up the big triangle, and as a result, A sub 0 would definitely be greater than or equal to the longest side of the other 3 triangles. Second of all, the longest side of a triangle is associated with the shortest altitude of that triangle, and therefore we can easily write the following expressions. A sub I times M delta I over 2 would simply be equal to S sub I, the area of that triangle I. And finally, the area of the whole triangle S sub 0 is simply equal to S sub 1 plus S sub 2 plus S sub 3. Now let's start plugging in, replacing these S sub i's with this expression here, which would imply that, so S sub 0 would simply be equal to A sub 0 M delta 0 all divided by 2, which is equal to, so S sub 1 would be A sub 1 M delta 1 over 2 plus S sub 2 would be A sub 2 times m delta 2 over 2 plus finally a sub 3 times m delta 3 all divided by 2. Now the 2's will cancel out, and dividing across by a sub 0 we would get m of delta 0 is equal to a sub 1 over a sub 0 m delta 1 plus a sub 2 over a sub 0 m of delta 2 plus a sub 3 over a sub 0 m of delta 3. And now recognizing that a sub 0 is greater than the others, a sub 1, a sub 2, and a sub 3, each one of these coefficients are less than or equal to 1. So as a result, if we replace them by 1, we would make the right hand side bigger. So m delta 0 would be less than or equal to m delta 1 plus m of delta 2 plus m of delta 3, and that was exactly what we needed to show, like here. So we are done with the first configuration. Now let's move on to the second configuration, namely if one of the three vertices ABC is inside the triangle where X is a vertex of that triangle. So in that case, we would have the following. So let me just, so this is case 2. So we have, let me just draw the picture quickly. So we would have ABC is inside and X is outside. So what would happen now is that because C, so let's write that down. So C is inside triangle ABX, and well, we don't need brackets. So C is inside triangle ABX, and now I make the following claim. Let me write that down as a claim. I claim that M of ABC, M of ABC, meaning the shortest altitude in triangle ABC, is less than or equal to M of ABX. Whenever a point is inside a triangle, then I claim this relationship holds. If, let me write that down, C is inside triangle ABX as we claimed, and the proof will depend on another casework. So case 1 would be that the longest side, so longest side is AB. Well, if the longest side is AB, then it means that in triangle ABX, the shortest altitude would be, let's call it X prime. Side is AB, then this implies X prime is shortest altitude. And in a similar way, if you focus on triangle ABC again, automatically in that triangle as well, AB would be the longest side. As a result, CC prime would be the, so CC prime is shortest altitude in triangle ABC. In triangle ABC. So this one was the shortest altitude in triangle ABX. Now the claim asserts that CC prime is less than or equal to XX prime, which is obvious, right? The drawing is clear. So this case was easy. The other case is slightly harder. So what happens if, let's say, XB is the longest side? So longest side of triangle ABX is BX. So what happens if the longest side is BX? So in that case, let's draw the triangle again, ABX and C inside. Let's probably draw it here. So longest one is this one, ABX. So BX is the longest one, and C is a point somewhere inside. Let's say it here, I guess, or yeah. So let's put C here. Then if the longest side, so this one is the longest, then I can drop an altitude. Oops. When I drop an altitude here, and then I have a triangle ABC, and I will go ahead and drop an altitude. So this is the point C. I will draw another altitude here on triangle ABC onto side BC. So I call let's call this the foot of the altitude of triangle ABX, starting from A as P. Yes. Or let's just call it A prime. Yeah, because it's opposite A. Let's just call it A prime, and let's call this altitude as A double prime. And the intersection point, I will simply call it as W. Now, because we have the right triangle WA double prime A, if you focus on that right triangle, it is obvious that A double prime is less than or equal to, actually it is strictly less than, but let's say less than or equal to AW, which is obviously less than or equal to AW plus WA prime, which is simply AA prime, right? And now the left hand side, AA double prime is actually it's not necessarily equal to, is greater than or equal to the shortest altitude of triangle ABC. And this one, AA double prime, because this is the longest, so it is definitely equal to, not less than or equal to, but rather equal to ABX. And that immediately implies the claim again, right? So regardless of the two will the proof is now complete for our original claim. So regardless of the configuration, if you have a situation where there's a point inside a triangle, then the shortest altitude of the triangle, the smaller triangle, will be smaller than the shortest altitude of the bigger triangle, outside triangle. So having proven this claim now we can solve the second configuration here, which we did, right? So the claim was expressly showing us that, well, okay, so the claim did prove this result. Now we can go back to the question, and the question is clear. ABC is less than or equal to MABX. So this is a much stronger result what we have proven here, right? So this claim would immediately imply the desired result, that MABC is less than or equal to MABX and the other two, right? So but just this one is by itself greater than this. When you add further things onto the right hand side, the inequality will be preserved. Now the final case, case 3, what happens if, like we did earlier, we have a convex quadrilateral where 4 points A, B, C, and X lie on the corners of that quadrilateral. Let's first draw the diagonals of this quadrilateral, and let's say that they meet at the point X prime. And according to the claim which we got earlier, we can easily say that M of BC X prime would be less than or equal to M of BCX, because X prime is inside triangle BCX. Well, inside or on the boundary, so this claim holds. And also, again by the claim for case that we produced for case 2, M of BAX prime again is less than or equal to M of BAX, which is again the same thing, BAX prime, if you focus on this upper triangle, and X prime is inside BAX, and this claim also holds. And finally, if one focuses on triangle ABC and considering the case 1 again, this would imply that M of ABC would be less than or equal to M of BCX prime,
plus m of bx prime a plus m of x prime ca. But m of x prime ca is simply equal to 0, so we are left with this expression here, and this expression will of course imply combining it with this one and this result. So MABC, the shortest altitudes of triangle ABC. Now I can replace this one with this expression here, M of BCX plus, and then this one can be replaced with that one, M of BAX, and that one was 0. And look at that. This would immediately imply the desired result, right? Because it is a stronger condition, right? So it definitely implies the desired inequality, right? It even misses one term, but it doesn't matter. It's already bigger than or equal to the shortest altitude of ABC. So we don't even need the third term here, which is apparently 0. So we have therefore considered all the three cases, and in all these three cases the given inequality is satisfied, and we are done. So hope to see you guys in our next video.